Shout out to the level heads in the chat. See the boys pulled up. See. All right. So we'll get into it here real quick. Let me give a little preface. So the other day I was talking to my buddy about the nature of the atomic model and how it kind of mimics a vortex. If you think about the instead of these being particles, they're just it's pressure mediation, or it's the direction of current flow for pressure mediation, high to low. So if you have a highly spinning or a highly dense charge potential vortex, right, spinning, you're going to have the high to low fluctuation within it. Um, so I was like, oh, okay, it seems very similar. So I started looking into it. Well, it turns out there's a history of this exact concept. So that's what we're going to get into tonight. I came across some stuff from Lord Calvin and his thoughts on the nature of what an atom is and compared to an ether vortex. So I was trying to get his book on it. I forget the title of it. It's mentioned in here. We'll go over here in a second. But I found this guy's thesis on it, and he did a nice. I was reading about 30 pages in, and it was like a really nice summation of the history of everything. So I thought it would be cool to read it out and go over it. So here is the vortex theory of atoms, pinnacle of classical physics. A thesis for the master's degree in history and philosophy of science by Stephen Vander Laan. All right, shout out to your boy Stephen Vander Laan. All right, so I'm just gonna kind of read through, give a little commentary here and there, but it's an interesting history. So abstract investigation into the 19th century atomic theory that assumed atoms to be vortices of an ether. Originally an idea of Calvin, the vortex atom theory enjoyed great popularity in England, roughly from 1870 to from the 1890. It had a good run, boys. It was a good couple of years, and then it died out, I guess. Real unfortunate, you know. So in this thesis, right around the time of Michelson Morley, real shame. Let's see, they had to bury it, I guess. In this thesis, the popularity of the vortex atom theory is explained through through four values in 19th century English physics. Furthermore, it will be argued that the surprising fact that the theory was virtually ignored by German scientists can be explained by a German critical attitude toward scientific theories, an attitude that was the reaction to the romantic philosophy of natural philosophia. Very cool. All right. Why is that highlighted like that? Oh, shoot. Okay. Sorry about that. Introduction into the vortex theory of atoms. Okay, so the wreckage of the rejected theories is appalling, but a knowledge of what actually goes on behind what we can see or feel is surely, if slowly being attained. From your boy Hicks. Shout out to Hicks. All right. In the first chapter, the vortex theory of atoms is introduced together with an overview of its history. After that, I will pose my research questions and give an outline of the structure of this work. So 1.1, ether and atoms. In the course of the history of the science, there is one concept that is notoriously connected to failed scientific theories, the concept of the ether. Although the although the ether was already present in ancient Greece, where it was uh, where it was to fill the vacuum of space and kept alive the work of uh, I can't remember this guy's name. Uh, Descartes or something. Descartes, the work of Descartes and Newton in the 19th century can be regarded as the golden age for the ether. It has said to It has to be said that scientists always remain somewhat suspicious towards the unfathomable ether, but during the second half of the 19th century, the existence of the ether was close to being undeniable. This was largely due to the development of the theories of light by Augustine Fresnel in 1818 and James Maxwell in 1861. It was through these theories that scientists became convinced that light was a wave-like phenomenon rather than a stream of particles. If wave, if light was a wave, then it needed a medium through which it could undulate. As water waves, it needs water, and sound waves like it needs air. Light also thought would require some substance as its carrier. The undulation of nothing was regarded as an unthinkable idea, right? So this idea of I can hand you a wave, but I can't wave you a hand. Yo, Andrew, that's what's up, bro. That's awesome. I'm glad to be a part of something that helped out like that, man. That's awesome. Um, so here we go with the idea of like w- I can hand you a wave, but I can't wave my hand or whatever, right? So light needs a medium to wave in, right? Everyone knew this. Now they redefined all of physics and all of that to make it so that they didn't need it, but before they lost their minds, it was an unthinkable idea. So next to the acceptance of the ether, the 19th century was also a deciding period for atomism. Although the idea of matter being comprised of minute finite building blocks is as old as the ether. Dude, that's kind of interesting. They're both super old theories if you think about it. Given like taking the history on face value, given the dates or whatever they give us for the guy that allegedly came up with atomism and all that. So it also always had even conceived with suspicion. Yet in the 19th century, science progressed to the point where its theories could reach the dimensions of the atoms and enabled scientists to deduce some of their actual properties. As these properties were being revealed, physicists used them as reference points to construct atomic models that could account for and describe the composition of matter. Three of these models were the atomic model of Dalton, the theory of force centers of Bosovich, and the vortex theory of atoms by William Thomson, better known henceforth and referred to as Lord Kelvin. So, boy, Lord Kelvin. So, 1.2, the vortex theory of Kelvin. It is the vortex theory of atoms which is the subject of current investigation, not because the other two theories are less interesting, but because of the little attention Calvin's theory has been given up until now. Besides minor references to these theories and to the theory and the studies of history of atom or ether, there are only three studies dedicated to the vortex theory of atoms. First is the paper by Robert Silliman from 1963, which is only a very general account for the theory, but nevertheless became the standard reference because it was only because it was the only account of the vortex theory available. In 1994, the dissertation of Alphonse Alchemade appeared, which contains a more thorough account of the history of the vortex. We'll have to check that out. Actually, I need to get my highlighter going. Oh no, what's wrong? Why can't I highlight? Oh, there we go. Come back to that. Okay, yeah. Mainly to introduce for the second part of the dissertation about the technical aspects of vortices and fluids. Nice. We'll definitely check that out. Finally, the most complete and recent work has been published in 2002 by Helgi Kronel. Yeah, shout out to that guy. Which also became a chapter in his book Higher Speculations, published in 2008. The title of this paper, "The Atom or the Vortex Atom: A Victorian Theory of Everything," gives a good characterization of the theory. Hang on one second. All right. Let's see. The idea of the vortex atom theory was to explain everything, just as some equations of fluid dynamics. Shoot, hold on 1 second. All right. Testing. All right, should be back. All right. So, theory of everything was it gives a good characterization. That's cool. And the idea of the vortex atom theory was to explain everything just with some equations with fluid dynamics. To quote the English physicist George Fitzgerald about the ambition of the theory, it would be true. Oh, if it be true, ether, matter, gold, air, wood, brains are but different motions, right? So different modality, different oscillations, different vibrational rates that are holding the structure together. Different vortices interacting that are repelling each other, so that you don't go through something. That there's like a physical interaction, different frequencies of vibration, right? So that's cool. In short, the vortex theory pictured small atoms as small vortices in ideal frictionless fluid, which it was often identified as the ether. First in the published, Calvin first published the idea in 1867 and kept working on it until the theory was abandoned in 1890. He was not the only physicist spending his time elaborating on the theory, in particular, together with J.J. Thomson, who discovered the electron, and William Hicks, another English physicist. Calvin formed the core group of the vortex theory. Yep, these dudes are pretty cool. Shout out to J.J. Thomson. And I'm not familiar with Hicks yet, but I'm sure we'll get acquainted here soon. Around these three men stood a group of scientists that are particularly, or that partly participated and published from time to time on the theory. Amongst these scientists are about a dozen of them were names like Peter Tate, George Fitzgerald, Joseph Lamar, Carl Pearson. Other British scientists like James Maxwell did mention vortex theory occasionally, sometimes favorable, but always somewhat doubtful. And he was always writing about it like, maybe these vortexes are cool, but I just don't know. He just wasn't ready for it. That's what's up. It's good to have some speculation, Maxwell. That's cool, man. He was doubtful of it. It's like noted throughout history. He was like, he never really was super on board. Let's see, 1.3. History of the vortex and the theory of atoms. That's my note from all that. That's my takeaway. All right. So Calvin had occupied himself with the idea of a hydrodynamical theory of everything already in the early 1850s, but there were two events that gave him inspiration for the vortex theory of atoms. First was the appearance of of a paper on hydrodynamics in 1858 from the German physicist Hermann von Helmholtz. Yeah, I think Helmholtz actually added a term to Maxwell's equations that allowed it to describe the divergence and convergence of the, what do you call it, torus field. So the geometry of a torus field could be described with Maxwell's equations with this guy's additions, if I'm not mistaken. Although he derived equations in this paper were a huge step forward in the theory of hydrodynamics. Oh yeah, that must have been it. So, yeah, obviously, it gained little attention at the time of this publication in Germany. Let's see. One person who did appreciate the work of Helmholtz was Peter Tate, a Scottish mathematician who in many projects was in close collaboration with Calvin. Immediately after its publication, Tate translated Helmholtz's paper into English for his personal use. Calvin, a close friend of Helmholtz, read the paper as well in 1858, but he did not see the significance until Tate published the English translation in the English Philosophical Magazine in the summer of 1876. Vortices. The mathematical theory of vortices in a fluid was until then still a very much in its infancy. It had already occupied the minds of Descartes, of Descartes, Euler, and some of the lesser known natural philosophers. But it was, but it was, but it was through the hands of Helmholtz that the vortex theory became established as a serious branch of fluid dynamics. In his paper, Helmholtz assumed an ideal fluid that is of an incompressible that is an incompressible fluid without friction. It is this ideal fluid Helmholtz derived that portions of the fluid that are stationary will remain stationary and vice versa. Portions of the fluid that are in rotation or in rotational motion will keep the rotation. This was an expected result since the fluid did not allow for the friction and there was no action available to change the fluid's momentum. As a result, the vortex, which is a portion of the fluid in rotation, which will always exist out of the same portion of the fluid, would be immune to dissipation. So it wouldn't lose its momentum and dissipate, i.e., would exist forever. Helmholtz also showed that the strength of the vortex defined the product between the logical circumference and the rational velocity, its constant, over the entire length of the vortex tube. See Figure 11. So here's a vortex tube. The strength of the vortex is defined as the local circumference of the tube multiplied by its rotational velocity at that point. Helmholtz showed that this strength is a constant over the length of the tube. So as a smoke plume is smoke ring is expanding or whatever, I'm guessing that's kind of what they're talking about. That's crazy. He just figured all that out with math. That's nuts. So consequently, a vortex tube could not let's see. Consequently, a vortex tube could not end inside of the fluid for either the rotational velocity or the tube circumference would be infinitely large. However, in a fluid enclosed by a wall, a vortex tube could end on that wall. More interesting, for the subject of the atom is the circumference that the tube could also end in itself, forming a continuous loop. The simplest in this case, vortex tube, would be circular. Let's see, and commonly known as the vortex ring. See Figure 1.2. As an illustration of the rings, Helmholtz remarked that this is easily studied by pulling a spoon through a cup of coffee. So, very cool. So there's Figure 1.2, the representation of the vortex ring. Oh yeah, let me show you the Huff vibration or whatever it's called, real quick, because it all looks very similar here. Yeah, the Huff vibration. Copy. All right. So this situation right here, and then atomic model. Looks very vortexy, you know? That's all I'm saying. So yeah, we're gonna see a lot of that moving forward. It's a really nice graphics. Very vortexy. All right, from theory Let's see, from theory to experiments to enthusiasm. All right. After reading Helmholtz's paper, Tate devised an experiment to create these vortex rings out of smoke in a controlled way. Witnessing the experiment was the second event that supposedly gave Calvin the inspiration for his vortex theory. Calvin's enthusiasm became clear in a letter to Helmholtz describing the experiment. Let's see. Just now, Wizard has have a displacement of everything. Wait, what the hell? Hold on. I have to know what this is. Vertebral vertebral movements, the vortexual movements, have displaced everything else. Since a few days ago, Tate showed me that Edinburgh Edinburgh made a magnificent or showed me in Edinburgh a magnificent way of producing them. Take one side of the lid of a box or any old packing box will serve and cut a large hole on the opposite side. Stop the side, stop the open side loosely with a cloth. Blah blah blah. Strike the middle of the cloth with your hand. If you leave everything smoking in the box, you will see a magnificent ring of smoke blow out. All right, very cool. When Calvin characterized the behavior of the single ring vortex as magnificent, then the interaction between the two rings. Let's see. Helmholtz showed Helmholtz showed Helmholtz showed that in his paper how the two rings in the vicinity of each other would interact, and Tate's smoke ring confirmed that these interactions to the approximate with a non-ideal fluid fit perfectly. So taking what dude had mathematically extrapolated, assuming perfect dynamics and stuff, to make the vortex go in perpetuity, he found that there was a close approximation for non-ideal material. Very cool. So, for instance, Helmholtz calculated that the two identical rings with opposite direction of rotation would slow down and both increase in size and direct upon directly approaching each other in such a way that they would never come in contact with one another. That's crazy. To come back and read that. Let's see. Two vortex rings heading in the same direction, one chasing the other, exhibit even more curious behavior. The ring in front will expand and slow down, while the rear ring will turn up its speed as it becomes smaller. If the initial conditions are right, the chasing ring can actually intercept the front ring, going through the middle of it and become the front ring. And then the whole process starts over again, leaving the ring. What? That's nuts. What? If the initial conditions are right, the chasing ring can actually intercept the front ring, going through the middle and become the front ring. That's crazy. And then the process starts over again. Playing a game of leapfrog. Wow. Wow. That's so crazy. I didn't. Wow. Okay. So, in the ideal theory and the non-ideal laboratory, these rings showed a remarkable stability. Calvin and Tate tried to dissolve the rings by cutting them in half with a knife, and he tried to let the rings violently collide with each other or with the walls. Yet the vortices let the blade go through quickly, uniting again and bouncing off of each other, and with the walls the with what bounce off each other, and with the walls the apparent perfect elasticity, so they would just bounce right off. These experiments certainly made a big impression on Calvin, and with the knowledge that the ideal fluid and the rings would be indestructibly or would be indestructible and would really collide with elastic, hypothesizing or collide elastically. Hypothesizing was very tempting indeed. Yeah, very tempting indeed. More like, dude, that's crazy that it has that interaction. It just plays leapfrog with itself. Let's see. Back to theory. The prime property, or better, the definition of an atom, always had been its indestructibility. The commonly accepted atomic model viewed atoms in a tiny indestructible spheres. Let's see. Tiny indestructible spheres. The billiard ball model. Calvin called this the I don't know, the Lucretian atom. I don't know. After the ancient Greek philosopher Titus Lucretius, I don't know, and it was let's see, and he was not content with this representation of the atom. In his first publication on the vortex of atoms, he severely criticized it for only pretext seeming to justify the monstrous assumption of infinitely strong and infinitely rigid pieces of matter. It seems necessary to account for the unalterable distinguishing qualities of different kinds of matter. Calvin's main objective to the billiard ball model was that its solidity prevented a natural exploration for the properties like elasticity. So it was a limited model that didn't really explain the observations that they were making. Right. Where on the muted, okay. On the vortex atoms, or where on the vortex atoms was a very qualitative paper. A year later, in 1868, Calvin published his second text on vortices, on vortex motion, which was a much more technical which was much more technical. It also became clear from this paper that the development of the theory of vortex atoms was accompanied with major progression of hydrodynamics. Calvin started this paper by stating that the mathematical work of the present paper has been performed to illustrate the hypothesis that space is continuously occupied by an incompressible frictionless liquid acted on by no force, and that material phenomenon of every kind depends solely on motions created in this liquid. Yet what follows are 53 pages of hydrodynamic equations that do not mention the atom once. Yeah, so your boy just was like, yo, it's all just a vortex. There's no atom. In the following years, for most scientists working on the vortex atom theory, this would be a general template for the text about the vortex atom theory, and an initial remark about the vortex atoms and how incredibly beautiful such a theory would be, followed by the investigation by some hydro. Let's see, followed by an investigation in some hydrodynamical problem. The theory for this approach is twofold. Firstly, as already mentioned, hydrodynamics was in need for some more thorough investigation. It was still somewhat in its infancy as a field of science. Secondly, mathematics needed to describe the behavior of vortices promised, the behavior of the vortices promised to be extremely complex. Secondly, the mathematics needed to describe the behavior of vortices promised to be extremely complex. Okay, got it. Where Calvin, in his
1967 paper typified the mathematical difficulties to be formidable. Maxwell described the difficulties with the not so optimistic term erroneous while reviewing the vortex atom in 1875 for the Encyclopedia Britannica. Oh, cool. Yeah, actually grab some encyclopedia. Encyclopedia, it's not a word. Some Encyclopedia Britannica uh, quotes on the ether. It was a really interesting review of it from 1937, I think it was. Maybe we'll go over that at the end when we cash out here. So we got a couple more to read. I'm just going to do about an hour here. Let's see. A good example of this formidable a good example of this formidable mathematics is found in a treatise on the motion of vortex rings, henceforth to referred to as treatise, published in 1882 by J.J. Thomson. Thomson at this time was just finishing his study at Cambridge, which was home to some of the world's best mathematicians, where every year the best students in mathematics were awarded the Wrangler titles. Although Thomson was not awarded the title of senior wrangler this year, he finished second best. Yeah, he was given an even more prestigious prize, Adams Prize, for his treatise, a prize for the best mathematical research given every year by the University at Cambridge to a junior student. In his treatise, Thomson followed the template, first making a few remarks about vortex atoms, followed by an impressive piece of hydrodynamical mathematics explaining the behavior of a single ring vortex, vibrating vortices, and the interaction between multiple vortex rings. So yeah, he was out there mathematically describing the leapfrogging and all that. That's dope. Um, so what mostly makes the treatise interesting, though, is the final chapter that deviates from the rest of the text, and it contains little mathematics and a lot of hypothesizing. In the title of the chapter, "The Vortex Atom Theory of Gases," gives a good idea of what this chapter is about. Although vortex theory of atoms is too much of a working hypothesis to give a clear idea of how Calvin and his followers pictured vortex atoms, the final chapter in oops, the final chapter in Thomas's treatise provides the closest thing to it. Yeah, that's really interesting because in the Adsutovsky Etherdynamics book, Adsutovsky's model of ether, he thinks that it's like a gas, in that when it's in this vortex motion, that's when it's acting like a particle because the vortex is the only thing that could maintain the structure of a molecular structure to even form a particle, for it to even have like physicality to it. So he thinks that the ether is made of these little things called amers, and these amers are like these little tiny vortices. So to pull up like a visual graphic for some gravy, it would just kind of be like, imagine this vortex, and then as if you can kind of zoom in here, see like, there's like these little branches off. You can see it's like made of little smaller particles. Imagine those are even little smaller vortices, right? And then they're all making a larger vortices. So like as a charge potential is increasing, the amount of these vortices that are formulating and compressing in on another vortice, I don't know, I'm vortici are that's how it's holding charge and momentum and all that kind of stuff. So it's kind of like a fractal breakdown. Oops, I need to zoom out of that. Nope, I just messed up real bad, Pop. Not sure what I did. That sucks. Oh wait, I can just redo. There we go. All right, cool. All right. Accidentally controlled Z without knowing what I did last. All right. So the treaties also make the treaties also mark the high point of the vortex theory of atoms. Around its appearance, Calvin and others published a great number of papers on this theory, and many prominent physicists spoke in awe of the idea of reducing matter to a few hydrodynamical equations In the same sentence where Maxwell called the mathematical difficulties of a vortex erroneous, he admitted the glory of surmounting them would be unique. Nice. So it was at this high point that the research in vortex theory was more or less taken over by the younger generation of English physicists like Carl Pearson, George Fitzgerald, and William Hicks. Because the vortex theory was proposed, because the vortex theory was proposed by such an eminent figure as Calvin, and that the theory promised to be the theory of everything just based on fluid mechanics, it could expect to capture the interest of most physicists. To arouse more than just the interest, though, the theory had to deliver some results, to explain a phenomenon or predict new ones. Yet this was lacking in the research of vortex atoms. Calvin and his followers made much progress in hydrodynamics itself, but from the start of 1867 until the mid 1800s, they could not deliver a satisfactory kinetic theory of gases, a theory of gravitation, or a theory of electromagnetism based on vortex atoms. Dude, the vortex atoms in the chat. Fucking chat. Let's see. I typed VO for vortex and it just went to volleyball. So I guess we get a volleyball. So, but imagine the volleyball spinning like a vortex. So vortex sponges. Around 1885, a new type of vortex theory emerged, the so-called vortex sponge theory. Instead of viewing atoms as consisting of small separate vortices, this type of theory supposed that ether was completely filled of tiny vortices, and these so-called closely packed vortices made a large sponge-like structure, which gave category to the theory of model. Dude, so is that not what I just described? That's crazy. Because I was like, didn't read as far as I thought I did in this paper, or I must have skipped ahead because I didn't read all of the extended stuff. I kind of skipped ahead to like around right here, I think, the vortex atom theory stuff. So this is crazy. So yeah, vortex sponge. Like I don't know, I'm kind of feeling the vortex sponge. I like it. So these closely packed vortices are made in a sponge-like structure, which gave the category for this name model. The difference with Calvin's original idea of the vortex sponge theory is that the atoms were thought to be constituted of larger sponge structures instead of single vortexes. The motion for the sponge theory was to have one ether for both atoms and electromagnetism. It was important to keep in mind that the vortex theory was partially motivated by the need for an ether theory, or sorry, by the need for an ether from other theories of physics, like theories on light and electromagnetism. The ether was presupposed to exist, to be existent, to be. The ether was presupposed to be existent. Calvin, though, did not at first speak of the vortices in the ether. He rather spoke of the universal plenum. Yo, what up, Evan? Let's see. Let's see. A universal plenum. But the ether would of course be the single best candidate for this plenum. Tell me you're the ether without telling me that you're the ether or whatever, right? So until the 80s, the 18th, until the 80s of the 19th century, Calvin and his followers were more or less allowed to freely speculate. They were allowed to freely speculate. That's cool about vortices and such of a universal medium. Yet the ether was originally a child of the theory of light and electromagnetism, and in some way, the ether theory of vortex atoms had been reconciled with the ether of these theories. The two ethers, or let's see, two ethers was in the context of unification regarded as undesirable. Let's see. Having two separate ether theories to explain the phenomenon like this. Yeah, got it. So, an ether containing the sponge like structures could, according to Hicks and Fitzgerald and Calvin, account for the transmission of light and other electromagnetic waves, something which was problematic in the early atomic theories of ether. In the 1888 lecture to the British Association of the Advancement of Science, Fitzgerald discussed the state in which the vortex theory was at the time. Although he spoke, man, although he spoke Although he still spoke hopefully about the theory, reading it in hindsight makes it clear that the idea of the vortex atom was already in decline. At the time, the vortex theory of atom was already over 20 years old and over 100 papers had been published on the topic, so it could be accepted that Fitzgerald was going to report on some of the progress made over the years. Yet it appeared from Fitzgerald's speech that if he had started from scratch with the vortex theory, or it appeared from his speech as if he had started from scratch with the theory. The text resembles much of Calvin's paper in 1867, which contained no detail on how certain phenomena could be explained. Fitzgerald gave only a general talk about how great and attractive the vortex theory of matter could be. The following quote may illustrate this. Hard particles are abominations. Perhaps perhaps the impenetrability of the vortex would suffice. The impenetrability of the vortex would suffice. That is that is all. No mention of any work by Calvin or Thomson who tried to develop a kinetic theory of gases from the work of vortex theory. Apart from that, the term abomination resembles strongly the monstrous assumption which Calvin used earlier. William Hicks, on the other hand, made more progress in the vortex theory. He repeatedly published new ether sponge theories and went on to a fair amount of detail to model about the electromagnetic theory based on ether sponges. Nice. Shout out to your boy. In 1895, he also gave a lecture for the British Association on the vortex theory of atoms, although it had already been long abandoned by Calvin Thomson and most other members of the scientific community. But your boy William Hicks was holding it down. At the beginning of his lecture, Hicks stated that to him there were two ways of dealing with the theory that is in trouble. One is to give up on the theory, and the other is to try and see if it can be modified to get over the difficulty. From the rest of his speech, it became very much clear that with the vortex theory of atoms, Hicks was willing to allow much modification to keep it out of trouble. Oh yeah, like okay. We'll have to see what he was willing to accept, right? So to cover up all of the problems and to cover up all of the problems and to include electromagnetism and gravity into the theory, Hicks proposed a new type of vortex sponge theory, the cell theory of ether. In short, the proposal was to assume that the ether was divided into tiny rectangular boxes containing a vortical current. Further details on this topic will be explained in the second chapter. Decline of the theory. Yeah, like if you're willing to put it in, that's some interesting modifications that he's willing to make. Have to hear more about that. Decline of the theory. The noteworthy paper was published on the theory after 1895. And from the foregoing history of the vortex atoms, it became clear that from Calvin's original idea in 1867 that the vortex theory of matter evolved to a collection of ideas as concerning single rings, multiple rings, vortex sponges, and cell and vortex cells. Nice. Is noteworthy in the paper published. Let's see. Is noteworthy. Oh, no noteworthy paper was published on the theory after 1905 or 1895, and from the foregoing history of the atom or the vortex atoms, I think it becomes clear that from Calvin's original idea in 1876, the vortex theory of matter had evolved into a collection of many ideas concerning. Okay, yeah, I got it. Okay. From Ludwig Boltzmann, the Australian physicist, a fierce promoter of the atomic model, a variety of different ideas was certainly not a blessing. Every second best physicist felt himself called upon to devise his own special combination of atoms and vortices and fantasy and I don't know. Oh, and fancied vortices and fancied having done so that he had pried out the ultimate secrets of the creator. Some special combination and fancy having done so that he pried out the ultimate secrets of the creator. Oh dang, that's an dude, that's a fucking that's interesting. Oh shoot. Okay, there we go. Pretty harsh criticism. Whether whether this harsh statement is justified or not, it is one of the very most few continental reactions of the vortex theory. It highlights an interesting historical fact about the vortex theory of atoms. The theory was almost exclusively an English affair. This is remarkable because although historians of science give the vortex theory or the vortex atom theory little attention in the second half of the 19th century, the theory was a significantly large research program in England. The book A History of European Thought in the 19th Century by the English 19th century historian John Mears also contained and remarked, the vortex theory is the most advanced chapter in the kinetic theory of matter, the most exalted glimpse into the mechanical view of nature. Though suggested by Helmholtz, it has already stated been limited and most exclusively to England. If science still shows international differences in patriotic predictions, this affords a new meaning, or this affords one of the few remaining examples. From this quote written in 1904, it becomes clear that some people like Mears remain hopeful about a theory long after it had been abandoned by the scientific community. So from this quote written in 1904, yeah, it becomes clear. Yeah, besides a handful of papers by a dozen or so notes on the vortex atoms, scientists in the United States, France, Germany practically ignored the theory. Helgar Kolver, Hel- Hegel, Helgi Krag also finds this most remarkable. He concludes that the theory was developed only by British scientists because of the zeitgeist of Victorian Britain, which he characterized by mathematical guided research with an accent on hydrodynamics and a desire for mechanical explanations of natural phenomenon, which combined with extra scientific ramifications in a theory. With extra scientific ramifications in a theory. See whether it was due to the absence of the specific spirit in Germany or the vortex theory was ignored by German physicists. In the conclusion, Krag does not draw. Yeah, so trying to explain everything with the mechanical like with an actual cause and effect relationship. Like, yeah, I can see how that would be appealing, right? Because nobody liked action at a distance, you know. So let's see. 1.4 research questions. So why was the vortex theory of atoms ignored by German scientists? Next to England, Germany was in the second half of the 19th century a major scientific research and the home of the most prominent physicists that worked on various hypotheses surrounding the atomic theory. Furthermore, the English the English interest in the vortex rings was instigated by a paper of Helmholtz, who was one of Germany's most prominent or most important scientists in the 19th century. Both Silliman and Krah do not attempt to explain the lack of German interest in the vortex theory. Uh, Alchemade Alchemade does give a hint and an explanation, suggesting that the vortex theory of atoms did not fit into the 19th century mainstream philosophical movement of Cantonism. Cantonism? Never heard of it. Neo Cantonism. To find whether. Yeah, what is that? Let's look at that real quick. That Neo Cantonism was sweeping through, huh? Philosophical movement, roughly until the first one. Let's see. Let's see. Neo Cantonism refers to and after both Kant. All right, so by its broadened definition, the term Neo-Kantianism names any thinker after Kant who both engages substantively with basic ramifications of his transcendental idealism and cast their own project, at least roughly within the terminal. Yeah, I don't know what the fuck any of this means. To a multifaceted, internally differentiated trend of thinking in the early 19th and 20th century. The School of Marburg is what is usually taught. All right, we'll have to come back to that. All right, so to find whether Alchemede's suggestion is correct, and if it is not correct, to look for the other explanation of the vortex theory of atoms, why it was ignored in Germany, is the main goal of this thesis. All right, cool. So where was the? I want to skip to the part I was reading. Was it? Let's see, I think it was around here. Okay. Sorry, I'm trying to figure out where I left off at. Or where I started at. Okay, so vortex sponges and hollow, I think it was right around here. Yeah. Second. Properties of gaseous molecules in the introductory chapter. The theory of the vortex atoms. Dang, I should have just started here. Because this is where I started. um, but I kind of wanted to get to, or kind of wanted to read the beginning part of it. So the vortex theory of atoms. Okay. So the properties of gases and molecules, as noted in the introductory chapter of the 19th century, was a decisive moment for both concepts of atoms and ether theory. While the ether theory got support from the theories, or while the ether got support from the theories about light and electromagnetism, atoms was a crucial assumption in another two important theories that emerged during the 19th century: the kinetic theory of gases and the chemist's law of definite proportions, where the kinetic theory of gases reached a more complete form in the end of the 19th century thanks to Boltzmann. Its foundations were laid out by David Bernoulli, Rudolf Clausius, and Maxwell with his formulation of Maxwell's distribution. The law of definite proportions, originally from the Frenchman Joseph Proust, states that a chemical compound always contains exactly the same proportions of elements by mass. Although in its original form the law was independent of any hypothesis about the atomic structure of matter, it suited Dalton's let me move this up. It suited Dalton's atomic theory very well, which appeared around the same time. The point is, the kinetic theory of gases and the law of definite proportions were, unlike electromagnetism, favorable to the belief of the existence of the atom, or in the terminology of scientists back then, of molecules. So this is all trying to come up with a way to describe the behavior of gas. So they're like, how do we do it? I think that gets into one of these guys was the ideal gas law guy. I think who came up with the ideal gas law? I think it was. Oh, okay, so I was way off. So yeah, not the guy mentioned here. So let's see. Although it's original, let's see. Where are we at on time? Coming up on an hour. All right, we'll have to pick up tomorrow. Actually, let me read this out and then we'll pick up tomorrow. Let's see. Although in its original law, let's see, the forming hypothesis, the structure of Dalton's atomic theory, which appeared around the same time, this kinetic theory of gases, unlike electromagnetism. Yeah, okay. So this was their they were all just trying to explain different phenomenon and needed things for different purposes. And when it was convenient to mathematically come up with a framework and make predictions and stuff, they uh, they would disregard certain theories for other theories, and they were trying to while simultaneously some people were trying to come up with a theory to merge them all together. Is where we're at. So we will pick up tomorrow, and we'll read out the rest because I wanted to get to at least this part because this is where I was reading last night. So from Calvin, J.J. Thompson, and then I stopped at Thompson. So we'll pick up tomorrow and see what these. We'll get more into it. But that was the introduction to the history of vortexual motion, and within the ether as a perturbation of the ether, to facilitate different mechanical motions, um, uh, storing charge potential, the movement of waves, all that kind of stuff. So, all right, thanks for joining me, and we'll pick up tomorrow. Yo, shout out to my boy Toby. We'll be doing ether cosmology tomorrow. I think, is it tomorrow? Hold on, it might not be tomorrow. Let me look at see where we're at. Ether cosmology. Yeah, yep. Today at 8:30, we'll be doing ether cos. So we'll be going over Bennett. We'll be doing a review of that of in the field part 2. We'll be talking a lot about that stuff. And then what's the other day I got? On Friday, I'm sorry, not Friday yet. Thursday, I have E equals MC squared, a breakdown of the history of that on Geos. You can check that out. And I'll be streaming that as well. And that'll be at 10 p.m. on Thursday. And then on Friday, we got Flat Earth Fridays on Twitter Spaces. and we will be attending, or I will be attending. I don't know why I said we, like I'm bringing an entourage of people. But I don't know what that means. I'll be attending, and you know, there's a new policy called "Bring Your Own Glober" that may or may not be enacted. So, look forward to those changes or whatever. Have a good night.